Okay, our favourites. We're looking at geometries. We've got urea. Is excreted by mammals and can be used as a fertiliser. Okay, I'm going to be brutal here. I do not care. Not interesting to me at all in this first part of the question. All I'm really interested in is the formula of urea, knowing what it looks like, knowing how it's arranged. So predict. Predict is what it's asking me to do. The electron domain and molecular geometries at the nitrogen and the carbon atoms, applying valence shell electron pair repulsion theory. Okay, so electron, that means you need to know what's the difference between the electron domain geometry and the molecular geometry. So the electron domain geometry is what we have in class sometimes referred to as the base geometry. We've called it the base geometry. It's basically what it's like assuming all bonds are present. Basically, it's looking at how many electron domains do we have. Now, the molecular geometry, this one is the secondary geometry. This one takes into consideration things like how many lone pairs do I have versus how many bonds do I have. Okay, so electron domain geometry at the nitrogen. The thing that is missing here, and the thing that will confuse you, is the electron pairs. So the first thing that you should always do when you are looking at a question, even if it's given to you, the structure on VSEPR, is add any missing electrons. Okay, so I've added the ones around the nitrogen and there are none missing around the carbon. So this means that my nitrogen, let's start with that one. My nitrogen has got 4 electron domains. 1, 2, 3, 4. Anything that has 4 electron domains is tetrahedral. Of the tetrahedral shape, of the 4 domains, only 3 of them are bonding and 1 of them is lone. Ooh, come back. Okay, so 3 bonding and 1 lone. Now, as soon as I add a lone pair, effectively I'm removing a bonding pair. Oh, I'm terrible today with this. Okay, so instead of having 1, 2, 3, 4, instead of having that tetrahedral shape, I'm taking a bond away to put the lone pair of electrons in. So now what I'm left with, and I'm sorry I'm not great at 3D drawings, is kind of that pyramid-y shape. Okay, so if you remember that pyramid-y shape, because it's got a triangle as its base, we call it trigonal pyramidal. Pyramidal because it's a pyramid, trigonal because it's got a triangle. So that would take care of our nitrogens. Then we've got our carbons. So let's go to, shall I get rid of some of this stuff so I'm stop confusing us with all these extra bits and pieces? Okay. Bit of a perfectionist, want to get rid of all the little dots and dots. So now that they are gone, I'm looking at just my carbon, no extra pairs of electrons. So here I have got 1, I have got 2, I have got 3 bonding regions. Because this is a double bond, I don't have a 4th bonding region. These guys here are locked together, they can't be separated. So they only count as 1 bonding region. Now if I've got 3 bonding regions, anything with 3 bonding regions means potential to bond, has an electron domain geometry of anything with 3. And we've just looked at that actually with the nitrogen. So this one here is trigonal planar. Now, why is this different? Because we said we've just looked at that actually with the nitrogen, and we have. This one's got 3 bonding and it's got 1 lone. It's still got 4 total bonding areas. This one doesn't have any lone, it's just got 3 total bonding areas. Now, because it's not got that lone pair of electrons, we don't have the additional repulsion that would have forced our bonds in our nitrogen, forced our bonds in our tetrahedral shape to squish down a little bit. So with our carbon, what we've got is a carbon here. We've got one bonding region out to this side, one bonding region out to this side, and one bonding region out to this side. So we've still got the triangle shape. So we've still got that trigonal. But we don't have the extra electrons at the top to squish the bonds down. So if we look at it from above, we'll see a triangle. But if we look at it from the side, all I'll actually see is carbon and whatever it was bonded to, nitrogen or oxygen. It'll look flat. So it's all in a plane, like looking at a piece of paper. So that's called trigonal planar. Okay, and this is not answering this question. This is still for up here.